Muktai is a MSc second year, third semester student at IIT Madras, and her topic is canonical form of orthogonal operators. Muktai.
Thank you, sir. Okay, hello all. I am Muktai Desai. My seminar topic is a canonical form of orthogonal operators. Uh, we will prove a theorem about a canonical form of orthogonal operators. Before that, we will see some definitions, basic definitions about orthogonal operators. So first one is the definition of orthogonal operator. So we have V as a vector space with an inner product structure. Uh, then a linear map T from V to V is said to be orthogonal if given vectors V, W from V, inner product of TW with TV that should be equal to inner product W with V. So that is the definition of orthogonal operator. Then we are seeing orthogonal matrix. What do we mean by that? So a matrix, a real matrix A, is said to be orthogonal if A transpose is identity and A transpose A is identity. Then let us see third definition. We are starting with a vector space V over a field F, and T is a map from V to V, which is a linear map. A subspace of V, W, say W, is said to be T invariant if image of W under T, that is a subset of W. Then we will call our subspace W as T invariant. So now let us ask this question to ourselves, that is every orthogonal operator necessarily diagonalizable over R? Before answering this question, let us see some facts. Uh, I have listed below. So the first fact is, if you have a B vector space with an inner product on it, and T is a map from V to V, which is an orthogonal map, then its matrix with respect to any orthonormal basis is orthogonal. So you can find this proof in any standard textbook. I am not proving this theorem here. Okay, the second fact is, for given a theta from 0 to pi, closed at 0, open at 2 pi, that interval, the matrix cos theta minus sin theta cos theta, uh, that represents a rotation by an angle theta of the plane R2, and second matrix is matrix that represents a reflection with respect to the line written here. So, okay. So with this, let us get back to our original question. Is every orthogonal operator necessarily diagonalizable over R? So for that, so the answer is actually no. So for that, let us take theta as pi by 2. So that this matrix will look like 0, minus 1, 1 and 0. And you can easily check that it does not have any eigenvalue, real eigenvalue. So forget about diagonalizability. It does not have even real eigenvalue. So we have a problem, right? So we will see one theorem uh, about the whenever we don't have like the operator, orthogonal operator, which is not a diagonalizable operator, we will see one theorem which says that we can find out one orthonormal basis. With respect to that basis, our matrix of T will look more simpler. So we will see that theorem later. Before proving that theorem, we will see two lemmas. So here is the first lemma. So that lemma says every orthogonal operator on two-dimensional real inner product space that can be represented by either a rotation or a reflection matrix the matrices we saw above. So we will prove this theorem here. So let us take V, a two-dimensional real inner product space, and T is a map from V to V, which is an orthogonal map. Okay. So let us fix one basis, which is an orthonormal basis of V. I am calling it as the B. And suppose matrix of T with respect to that basis B is equal to ABCD, this matrix. Since because of our fact 1 that we saw, uh, since our T operator T is orthogonal, this matrix is also orthogonal, and that's why matrix of T with respect to that basis uh, into matrix of T transpose, that will be equal to identity. So from that calculations we get a square plus b square is equal to 1, and c square plus d square is equal to 1, and third equation, because a square plus b square is equal to 1 and c square plus d square is equal to 1, we have these relations. We can find out theta and phi from 0 to 2 pi, closed at 0, open at 2 pi, such that a is equal to cos theta and c is equal to sin phi. Since A and B are on the unit circle centered at origin, similarly C, comma D, that point is on the unit circle. So we can find out such theta and phi. Uh, okay, so from that, uh, putting these values in those equations, we can get B is equal to plus or minus sin theta and D is equal to plus or minus cos phi. Okay, so now we will consider the cases. So there are four cases in total. So first one is when B is equal to minus sin theta and D is equal to cos phi. Uh, okay, so I am putting those values in the third equation, AC plus BD is equal to 0. That gives me this equation cos theta sin phi minus sin theta cos phi is equal to 0. From that, I am getting theta minus phi minus theta is equal to 0, because I am choosing theta and phi from this interval. This is the only possibility. Okay, so by substituting the values, my matrix of T with respect to the basis, it looks like this, which is actually a rotation matrix. Similarly, second case, I am considering B taking value sin theta and D taking value minus cos phi. With respect to these values, our matrix of T with respect to that basis, it will be a reflection matrix. So these are the two cases. So the two cases are remaining, but one can check that the remaining two cases also show that matrix of T with respect to that basis is either a rotation matrix or a reflection matrix in R2. So we proved our lemma that every orthogonal operator on two-dimensional real inner product space, it can be either represented by either a rotation or a reflection matrix. Okay, so we will prove another lemma 2, before proving our main theorem. So that lemma says, let us take V, a non-zero set V, which is also finite dimensional real vector space, and T from V to V is a linear map. Then it says that V has T invariant subspace, say W, such that dimension of W is either 1 or it is 2. So we'll prove this lemma first. Before proving this lemma, we will first see the complexification of vector space and complexification of real operator, linear operator. So we are seeing this. So let us see complexification of R vector space V with two operations plus and dot. So what do I mean by that? I will construct one new vector space, that is V. I am calling it as a VC, such that that VC with two new operations will form a C vector space. So how I am going to do that? So let us take VC as V cross V, Cartesian product of V with itself. Now I am defining two new operations on VC such that to make it C vector space. So first one, I will define plus C, that is a function from VC cross VC to VC. So how I am defining that? You take vector u1 u2 from VC, another vector v1 v2 from VC, such that you how you are adding those vectors. So u1 u2 plus v1 v2 is equal to u1 plus v1 and u2 plus v2. So this plus corresponds to our plus in R vector space that we started with. Similarly, I am defining the operation dot, which is a scalar multiplication, that is a map from C cross VC to VC. How I am defining that? I am taking a complex number from C and a vector u1 u2 from VC, and this product scalar multiplication, I am defining it as lambda1 u1 minus lambda2 u2 and comma lambda1 u2 plus lambda2 u1. One can easily check that VC with these two operations plus C and dot C is indeed a C vector space, and observe that the way in which we are multiplying the scalar multiplication we are doing, and compare this multiplication with multiplication of two complex numbers. So okay, so we got one new vector space VC, which is actually a C vector space. Now we will see what is the meaning of complexification of R linear map. So our R linear map is T from V to V, where V is a real vector space. So complexification of T, I am denoting it as a TC. It is a map from VC to VC. So actually VC is complexification of our vector space V. So how I am defining that map? For given a vector u1 u2 from VC, TC of that vector is nothing but T of u1 comma T of u2. So T is actually R linear map. So this is how I am defining TC. So one can check that TC is a C linear map. So with this, I will prove the lemma 2. Okay, so now what we have? Firstly, we had a vector space V, which was a real vector space, and operator, which was from T V to V, which was a R linear map. From that, we made one new vector space VC, which is a C vector space, and a map TC from VC to VC, which is a C linear map. Now, by fundamental theorem of algebra, we know that this complex C linear map TC will have an eigenvalue. I am calling it as lambda 1 plus I lambda 2 from complex number. So it will have one eigenvalue from complex number. Okay, so I can find a non-zero vector, say uv from vc, such that tc of u comma v is actually lambda 1 plus I lambda 2 dot c into dot c u comma v. So okay, so now I'm applying the definition of TC. So that gives TU comma TV is nothing but this right hand side. So by comparing the components, uh, first component will give me TU is equal to lambda 1 u minus lambda 2 v, and TV is lambda 1 v plus lambda 2 u. Now I am considering one subspace W, which is actually okay. So how I am defining that W is a span of u comma v. So I am taking span over real field. So this W will be a subspace of V, which is a real vector space, and we can check that it has a dimension either 1 or 2. Okay, and because of this star equations, one can easily check that W is actually T invariant subspace, where T is our R linear map that we started with. So what did we prove? we proved that given a finite dimensional real vector space and an operator on it, we can always find out a subspace W such that it is a T invariant subspace of V and it has a dimension either 1 or 2. So with these two lemmas, we are now ready to prove our theorem. So we'll see the statement of the theorem. Okay, so here is the statement. Okay, we are starting with a non-zero finite dimensional real inner product space, and T from V to V is an orthogonal linear map. Then we are saying that there exists an orthonormal basis of V with respect to which our matrix of T will be a block diagonal matrix such that each block on the diagonal is one of the three matrices given here. Uh, Either it is 1, minus 1, or it will be cos theta minus sin theta cos theta. Actually, this is a rotation matrix where I am taking theta from this set written out here. So, okay, we will prove this theorem. The main idea is to use induction on the dimension of V. So, let dimension of V is equal to n. So, we will firstly consider two cases which are the base cases. So the first one is dimension of V is equal to 1. Okay, so we started with non-zero vector space. We can choose a unit vector u from V. Since dimension of V is equal to 1, this unit vector u will span our vector space, and the set singleton u that becomes an orthonormal basis of V. So say that set singleton u is equal to B. Then the matrix of T with respect to that basis, that will be 1 cross 1 orthogonal matrix. And by using the definition of orthogonal matrix, we can check that matrix of T with respect to that basis, I am taking square of that, that will be 1. That will give me matrix of T with respect to that basis is either 1, 1 cross 1 matrix, or it is minus 1. So we are through because we got our required form. Okay, so let us consider the second case. So dimension of V is equal to 2 here. Uh, so since our dimension of V is 2 and T is a map from V to V, which is an orthogonal map, by lemma 1, given any orthonormal basis B of V, we can always find out the theta from this interval such that our matrix of T with respect to that basis is either a rotation matrix or a reflection matrix. This is precisely what we proved in our lemma 1. Okay, so now we are considering cases. So, okay, if theta is equal to 0 or pi, let us see what happens. Okay, if theta is 0, then this matrix will be identity matrix, right? And this matrix will be 1, 0, 0, minus 1, which is in the required form because each diagonal block is has entry 1 or minus 1. So we are done. If theta is equal to pi, similar thing happens. So for this case, theta is equal to 0 or pi, we are getting our theorem's conclusion. Whenever theta is from this set, open interval 0 to 2 pi minus singleton pi, and if matrix of T with respect to that basis is a rotation matrix, we are good because we wanted that only. So if this is not the case and matrix of T with respect to that basis is a reflection matrix, then we observe that see, this matrix is a symmetric matrix and is a real symmetric matrix, and hence by a spectral theorem, what does it say? Every symmetric matrix is orthogonally diagonalizable over R. So here we have our symmetric matrix, that is a reflection matrix. So our operator T is also orthogonally diagonalizable over R. Because of this, there will exist an orthonormal basis B dash such that matrix of T with respect to that basis B dash, it will be of the form lambda 1 0 0 lambda 2, where lambda 1 and lambda 2 are real eigenvalues of our operator T. And see that the matrix of T with respect to this basis B dash, it will be again an orthogonal matrix. So by definition of orthogonal matrix, we will get that lambda I is equal to 1 or lambda is equal to minus 1, where I is either 1 or 2. Okay. So here also we got our required form. By these two cases, what did we prove? Whenever dimension of V is equal to 1 or dimension of V is equal to 2, uh, we get the conclusion of our theorem. So we proved our theorem for these cases. So these are our base cases. Now we will see what is our inductive hypothesis. It says for a given finite dimensional real inner product space V with dimension of V uh, is greater than or equal to 2 and less than n, and given an orthogonal map from V to V, the theorem is true. What does that mean? That is, there exists an orthonormal basis of V. With respect to that basis, matrix of T will be a block diagonal matrix such that each block on that diagonal is one of the three matrices, 1 minus 1 or 2 cross 2 matrix, rotation matrix, right? So this is our inductive hypothesis. Okay, so we are going to third step. So let us consider dimension of V is equal to n, it is greater than 2, because for n is equal to 2 and 1, we already proved our theorem. So we are starting with a vector space V with dimension greater than 2, and T from V to V is an orthogonal linear map. So for this vector space V and for this map T, we will by lemma 2 we will get uh, a subspace of U such that that subspace U is T invariant, and dimension of that subspace U is either 1 or 2. Okay. So now we are considering two cases. Suppose dimension of U is 1. Then we will again do the same thing that we did in our first step. We will choose a unit vector U from this vector subspace U. The linear map T restricted to U is well defined. Why? Because U is T invariant, this map is well defined, and one can check that it is actually orthogonal on U. So let us say B is equal to a singleton set U. So this U will again form a orthonormal basis of U, and matrix of 2 T with respect to that basis B, restriction map, this map, that matrix will be of the form 1 or minus 1. So we are good. Okay. So let us consider second case. Suppose there does not exist any one dimensional T invariant subspace of V. So our subspace U that will have dimension 2. So again, using first step, we can choose an orthonormal basis of U, say B, such that there will exist one theta from this open interval 0 to pi, for which T restricted to U, this operator, the matrix of this operator with respect to that basis, it will be of the form rotation matrix. So the question is, why is matrix of T restricted to U with respect to this basis is not a reflection matrix? So I am not answering this question right now. You can think, and the answer is not very difficult to see. So the hint is this matrix is symmetric matrix. Okay, so from both the cases, we find an orthonormal basis B of U our T invariant subspace U such that uh, uh, size of that basis is either 1 or 2. Okay. Okay. So we found out our subspace U, which is a T invariant subspace, and T restricted to U is an orthogonal map on U. So that's why it is a invertible map. So I am using this. So for given a U, say U dash from that subspace U, because of this map is invertible, there will exist one U from capital U, that is a vector subspace, such that T of U is equal to U dash. Now what I am proving is U per, that is a orthogonal complement of U, is also T invariant. Since we are in a inner product structure, we can always talk about U per, that is an orthogonal complement of a subspace. So now I will show that U per is also T invariant. For that, I am starting with any vector V from U per. So I have taken U dash arbitrarily from U, and now I am taking any vector V from U per. So what I want to actually show is TV also belongs to U per. So I am starting with inner product TV with U dash. That is nothing but TV, inner product of TV with TU. Since our orthogonal map is orthogonal, this will imply that TV inner product with TU is same as inner product of V with U. And since U was from subspace U and V was from U per, because by the definition of orthogonal complement, we will get inner product of TV with U dash is equal to 0. So we showed that for any vector V from U per, TV also goes to U per. So this is how we proved U perp is T invariant. Okay. So now you restrict our original map T to this subspace U perp. This will be again a orthogonal operator on U perp, and since dimension of U is either 1 or 2, dimension of U per will be strictly less than dimension of V. So we can apply our induction hypothesis to U per. So by induction hypothesis, there will exist an orthonormal basis, I am calling it as a B per, of U per, such that matrix of T restricted to U per with respect to this basis B per, that will be in the our required form. Okay. Since we are in an inner product structure, we can always decompose our vector space V as U direct sum U per, where U is a subspace of V. Okay, here we found out a basis, orthonormal basis of U per, and in the okay, and we also found out an orthonormal basis B of U as well. So now I am defining B1 as B disjoint union B per, and this actually forms an orthonormal basis of V, and by the construction of B1, matrix of T with respect to B1 looks like on the diagonal, first entry is T restricted to U with respect to basis B, and second diagonal entry is T restricted to U per that matrix with respect to B per. So this matrix is in the required form, and this matrix is also in the required form. So matrix of T with respect to B1, this is also in the required form, and this is how we proved our theorem by induction. Okay. So long story short, for given an orthogonal operator, we found out one basis, orthonormal basis of V, such that with respect to that basis, matrix of T is nearly diagonal, and the entries on the each diagonal block is either 1, -1, or a rotation matrix. So this is what we proved. So I have used these references uh, for my preparation. Okay, thank you. You can ask any questions and any doubts.
Yeah, Mugdha.
Yeah, can you go to the thing where you have written sine of theta minus phi is 0 or something like that?
Yeah, yeah, sure. Yeah, this thing, right?
Yeah. Okay, I think phi minus theta can be pi or minus pi also.
Okay.
Still, the matrix will look nice, but
Yeah. Okay. Okay.
hmm.
Okay. Yeah. Yeah. Correct. So even the theta phi minus theta is pi or minus pi, the matrix will look like either a rotation matrix or reflection matrix. So there is any problem in that.
Thank you, Muktai. Any other questions, suggestions, comments?
Yeah. So, Mukta, you used this complexification, no?
Yes. Yes.
Can you go to the definition of
Yes. Sure. Yes.
yeah? So
Complexification of vector space, right? R vector space. Yeah.
yeah. So
Huh.
will it be true for any finite field over some finite field also? Like if we remove R and put some FP, say finite field,
Huh. Huh.
will
Huh.
it be true then? Like your V
Uh,
is your FP vector space. Now I want a two-dimension extension. Like here also you did that.
huh. Huh.
Yeah. Will it be true there also?
Yeah. I have to think, but my guess is yes. It will be.
Yeah. So then there will be no special thing over 2, but you can extend for any n, right? You can generalize that. Like
Yeah.
n many cross product of this VC.
Yeah. 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 So we have to define the multiplication in a wiser way, I guess.
Uh, yeah, yeah.
Huh.
So yeah, that is yet to be checked. Yeah, correct.
Yeah.
So for
That
2, it is
might create a problem.
yeah, yeah. That might create a problem.
Hmm.
Okay. Like viewers may check that whether we can extend it to n dimension that thing or not. Yeah,
Yeah, sure.
I'm done, Tiranda.
Okay. So thank you. Let us thank the speaker, Muktai.